Hi everyone, this is Kiranmai from H&S department. Today in this session, we are going to discuss about semiconductor physics, in which we are going to see how the energy bands are formed in a solid materials. In this session, we are going to discuss about formation of energy bands and how the solids are classified into conductors, insulators and semiconductors depending upon the energy bands. First of all, when you take an isolated atom, electrons are tightly bounded and have discrete shape, discrete sharp energy levels. Everyone is well known with the structural figure of an atom, which is having a center nucleus. Around that, electrons are arranged in a particular shells. Depending upon the atomic number, the shell number will go on increasing. Now, in case of single atom, the electrons are individually moving in their energy levels and they were uh, bounded to the parent atom. When you take a metal or a solid containing large number of atoms, they are very close to each other. So the interatomic distance decreases and they allow energy levels of electrons of one atom to overlap with these or those of neighboring atoms. Hence, in solids, the energy levels corresponding to any one quantum number splits up into many closely spaced levels, thus forming bands of energy. So suppose when you take two sodium atoms, sodium which is having atomic number 11, which is having the electronic configuration of 1s2, 2s2, 2p6, 3s1. Now, when you draw the energy, atomic structure of sodium, this is sodium nucleus around surrounded by 1s2 electrons, 2s2, 2p6 electrons in second shell, and 3s1 electron in the third shell. Since it is a valency electron, this shell is otherwise called as valency shell, and the outermost shell around the valency shell is called as conduction shell. Now consider one more sodium atom which is having the same electronic configuration with three different shells, that is 1s2, 2s2, 2p6, 3s1, around that one empty shell. Now, when these two sodium atoms come together, what happens? The energy levels of both sodium atoms overlap with each other and forms energy bands. This is E1 energy band corresponding to E1 energy level of first sodium atom and E1 energy level of E2 second sodium atom, forming E1 energy band. Similarly, E2 energy level of first and second sodium atoms overlap with each other because they are having same energy. Again, they form second energy band called as E2 energy band. Similarly, the valency shell of first sodium atom and valency shell of second sodium atom together forms valency band, and conduction shell of first sodium atom and conduction shell of second sodium atom combinedly forms conduction band. And the gap between these two bands is called as energy gap. Now, when you see this E1 and E2 energy levels, these are fully filled levels where they won't compensate or they won't participate in the conductivity process, whereas this valency band electrons, which are single electrons, unpaired electrons, they are ready to excite to higher energy levels and they participate in conduction. So hence, these valency band and conduction band has very much importance in the determining the conductive properties or electrical conductive properties of the material. So the width of this band gap depends on the degree of overlap of electrons of the adjacent atoms and is largest for the outermost atomic electrons. The electrons in the lower energy bands are of no importance in determining the electrical properties of the cells because they are paired up electrons, whereas the electrons in the outermost bands of the solid are more determining many of the physical properties of the solid because they are the unpaired electrons. By giving a small energy itself, we can make them out of the atom so that they can go for conduction. Therefore, the allowed energy bands are valency and conduction bands. The band corresponding to the outermost orbit is called conduction band, and next inner band is called as valency band. And the energy gap between these two allowed bands is called as forbidden energy gap, where the electrons cannot have any energy values. So valency band is occupied by valency electrons and conduction band which is vacant at 0 degree Kelvin. According to the width of the gap between the valency band and conduction band occupation by electrons, all solids can be classified broadly into three categories, namely metals, semiconductors, and insulators. So in solids, gap between the two outermost allowed energy bands depends on equilibrium spacing between the atoms. First of all, let us see what are insulators. Insulators are the materials or the solids which are having an energy band gap about 5 to 10 electron volts, and it is virtually impossible at all the practical temperatures to thermally excite an appreciable number of electrons across this gap from the top of the highest filled valency band to the bottom of the lowest empty conduction band. And this means where the energy gap between the valency band to conduction band is very large in insulators. So at low temperatures or at normal temperatures, it is not possible to excite the electrons from valency band to conduction band. Hence, the current conduction in insulators is almost all zero at normal temperatures. So at very high temperatures only, electrons can attain an energy to excite from valency band to conduction band to overcome the gap that is about 5 to 10 electron volts between the valency band to conduction band. And the best example for the insulating material is diamond with an energy band gap of about 7 electron volts. Hence, diamond is bad conductor of electricity. Come to the second type of solid materials, that is a semiconductor, where the band gap between the highest filled valency band and lowest empty bands is quite small, say in the order of 1 electron volt or less. Then there will be an appreciate number of electrons that will be excited thermally from the states near to the top of the filled band to the states near the bottom of the next empty band across the band gap. So the best example for these semiconductors is germanium with an energy gap of 0.78 electron volts and silicon with an energy gap of 1.21 electron volts. Uh, but as you see the semiconductor materials, there will be a small energy gap between valency band to conduction band. So at small temperatures or at the normal room temperatures, we can easily excite the electrons from valency band to conduction band as the energy gap between them is very small. It does not need very high temperatures to excite the electrons from valency to conduction band. It needs in very normal and low temperatures. Hence, semiconductors can be operated at room temperatures as a conductor very easily. And current controlling in these semiconductors is very easy. Depending upon temperature itself, we can control its current. And all semiconductors will become insulators as the temperature approaches to absolute zero, which means that as you won't give any temperature to the semiconductor materials, there is no excitation of electrons from valency band to conduction band. Hence, semiconductors at absolute zero behaves like an insulator. At sufficiently high temperatures, all insulators must exhibit semiconductor behavior. Coming to the last type of solid, that is a conductor, in which a great number of free electrons are available in the outermost valency band, which is partially filled, then those solids are called as conductors. And they conduct electricity at all temperatures, and the electrical conductivity of conductor is much larger than the semiconductor and large concentration of free electrons. Hence, these materials are mostly used for conducting purpose, and insulators are used for the insulating purposes. On the screen, you can view the energy band gap between the three different materials, metals, semiconductors, and insulators, where insulators is having a very high energy band gap, where in metals, both valency and conduction band are overlapped with each other. Whereas in semiconductors, a very small energy gap is there between valency band to conduction band. Thank you.